It is a remarkable thing to consider how the world has been reshaped, in what amounts to the blink of an eye, historically speaking. The device in your hand, the screen you are likely reading this on, is the culmination of a journey that began not so long ago with a simple, almost accidental discovery. Our story starts in the year 1800 with an Italian physicist named Alessandro Volta. He was not trying to invent a power source for a future world of gadgets. Instead, his work was born from a scientific disagreement with a contemporary, Luigi Galvani, who believed that animals produced their own animal electricity. Volta set out to prove that the electricity came not from the animal, but from the contact between two different metals. To demonstrate his theory, Volta created what he called a voltaic pile. It was an elegant, almost humble construction. He stacked pairs of copper discs, zinc discs, one on top of the other, separating each pair with a piece of cardboard, cloth that had been soaked in brine, salt water. When he connected a wire to the top and bottom of this stack, a steady, continuous electric current began to flow. This was unlike the fleeting, unpredictable sparks of static electricity that were known at the time. For the very first time in human history, we had a reliable, man-made source of electrical energy. This simple pile of metal and salt water was the world's first true battery. The invention of the voltaic pile was not merely a scientific curiosity. It was a fundamental breakthrough that unlocked the door to a new age of experimentation. Before Volta, scientists could only study the brief, chaotic bursts of static electricity generated by friction. Now, they had a tool that could provide a consistent and controllable flow of electrical charge. This steady current allowed researchers across Europe to begin probing the very nature of electricity itself. It enabled them to conduct experiments with a level of precision and duration that was previously unimaginable, laying the essential groundwork for every single electrical discovery that would follow in the decades and centuries to come. Without this foundational step, the entire field of electronics would simply not exist as we know it. The battery provided the means to power the experiments that would uncover the deep and mysterious relationship between electricity and magnetism. For 2 decades after Volta's invention, electricity remained a fascinating, but somewhat isolated phenomenon. It could create chemical reactions and produce a steady current, but its full potential remained hidden. That all changed in 1820. Thanks to the observant eye of a Danish professor named Hans Christian Ørsted. He was in the middle of a lecture, demonstrating the heating effects of an electric current from a voltaic pile. On his table, by pure chance, lay a simple magnetic compass. As he completed the circuit and sent the current flowing through the wire, Ørsted noticed something extraordinary. The needle of the nearby compass twitched and deflected from its northward pointing position. It was a subtle, almost imperceptible movement, but its implications were monumental. When the lecture concluded, Ørsted was captivated by what he had witnessed. He spent the next several months in his laboratory, meticulously repeating and refining the experiment. He confirmed his initial observation. Whenever an electric current flowed through a wire, it produced a circular magnetic field around that wire. When he reversed the direction of the current, the compass needle deflected in the opposite direction. He had discovered a deep, intrinsic connection between two forces of nature that had, until that moment, been considered entirely separate. Electricity was not just electricity, and magnetism was not just magnetism. They were two sides of the same fundamental coin, locked in an invisible dance. Ørsted published his findings in a short paper, which quickly spread throughout the scientific community in Europe. The discovery electrified researchers and inventors. It was the first proof that one could use electricity to create motion, to exert a physical force at a distance. This principle, the interaction between an electric current and a magnetic field, is the very heart of the electric motor. The idea that a wire carrying a current could make a magnet move was a revolutionary concept. It suggested that the controlled flow of electrons could be harnessed not just for light or chemical reactions, but to do physical work, to turn wheels, and to power the engines of a new industrial age. This revelation was the crucial second step in our journey. Volta gave us a source of electricity, but Ørsted showed us what it could do. His discovery transformed electricity from a passive curiosity into an active, dynamic force, opening a vast, new frontier. The simple observation of a twitching compass needle was the conceptual birth of the electric motor, the generator, and countless other devices. Ørsted had shown that electricity could create magnetism. This led the great English scientist Michael Faraday to ask a beautifully symmetrical question. If a current could create a magnetic field, could a magnetic field be used to create a current? For nearly a decade, this question consumed him. He embarked on a series of brilliant and methodical experiments, driven by an intuition that nature's laws possessed a certain harmony. In 1831, he finally found his answer. In a landmark experiment, he wrapped two separate coils of insulated wire around a single iron ring. He connected one coil to a battery and the other to a galvanometer, an instrument designed to detect even the faintest electric current. When he connected the first coil to the battery, he observed a momentary surge in the galvanometer, connected to the second coil. And then something just as important happened. The current vanished, even though the first coil remained powered. When he disconnected the battery, he saw another brief surge in the galvanometer, this time in the opposite direction. The key insight was that a steady magnetic field did nothing. The current was only produced when the magnetic field was changing, when it was being turned on or turned off. He then demonstrated this more directly by moving a bar magnet in and out of a coil of wire. The motion of the magnet alone was enough to induce an electric current in the wire. He called this phenomenon electromagnetic induction. This discovery was perhaps one of the most significant in the history of science and technology. Faraday had found a way to convert mechanical energy, the energy of motion, directly into electrical energy. Ørsted had shown how to make a motor, but Faraday had just shown the world how to build a generator. This principle meant that humanity was no longer reliant on chemical batteries for its electricity. We could now generate vast quantities of electrical power by simply turning a coil of wire inside a magnetic field. All you needed was a source of motion, whether it be the force of falling water, the pressure of steam from burning coal, or the power of the wind. The practical consequences of this discovery are all around us today. Electromagnetic induction is the fundamental principle behind nearly every power plant on Earth. It is the reason we can plug our devices into a wall outlet and receive a steady, seemingly limitless supply of energy. Faraday's work also led to the invention of the transformer, a device that can efficiently increase or decrease AC voltages, essential for long-distance transmission. Without Faraday's persistent and elegant investigation into the symmetry of nature, our world would be a much darker and quieter place. He didn't just discover a law of physics. He handed humanity the key to mass-producing electricity itself. By the latter half of the 19th century, the principles of electricity were becoming well understood, and the ability to generate it on a larger scale was in place. The next great challenge was to find a practical, everyday use for this incredible power. While arc lamps existed, they were too bright, harsh, and dangerous. The dream was to create a safe, reliable, and affordable form of electric lighting that could replace gas lamps and candles. This was the challenge taken up by the American inventor Thomas Edison. He was not the first to work on an incandescent bulb, but he approached it as a complete system, power generation and the filament inside the bulb. Edison and his Menlo Park team tested thousands of materials to find the perfect filament. They needed something that would glow brightly and not burn out too quickly. After countless failures, in 1879 they succeeded with carbonized cotton sewing thread. The thread inside a pumped glass bulb created a warm, steady light for over 13 hours. This was the breakthrough. A light that was long-lasting, safe for indoor use, and mass-producible. Edison's genius was commercial. He built the whole system. He knew a bulb needed a reliable network. So he designed and built generators, insulated wiring, fuses, switches, and meters. In 1882, Pearl Street Station in Lower Manhattan went online, supplying DC power to 59 customers, lighting a small section of New York City. The world's first commercial electric utility. It proved electric lighting could be a scalable business. Practical electric light transformed civilization. It extended the productive day, letting factories and businesses run around the clock. It made city streets safer at night, reduced crime, and encouraged social life after sundown. Inside homes, it replaced flickering, sooty, and fire-hazardous flames of gas lamps and candles with clean, convenient, and consistent illumination. The light bulb was the first killer app for electricity, driving its widespread adoption and convincing the public. Edison's enduring glow did more than light a room. It lit a new era of human progress. Transition. While Edison was busy wiring cities for light, another profound electrical mystery was being explored in a German laboratory. James Clerk Maxwell had developed equations unifying electricity, magnetism, and light, predicting electromagnetic waves, energy traveling through space at the speed of light. It was a stunning piece of theoretical physics, but for 2 decades it remained a theory. No one had generated or detected such waves. That task fell to a German physicist named Heinrich Hertz. In 1887, Hertz devised a clever series of experiments to put Maxwell's theory to the test. He constructed a transmitter, essentially a high-voltage induction coil connected to a spark gap, 2 small metal spheres separated by a tiny bit of air. Hertz's experimental setup, spark gap transmitter and loop receiver. When a huge voltage was applied, a spark would jump across the gap. According to Maxwell's theory, this oscillating spark should radiate electromagnetic waves into the surrounding space. To detect these waves, Hertz created a simple receiver, a loop of wire with its own tiny gap. If the waves were real, they should induce a current in the receiving loop, causing a minuscule spark to jump across its gap. With his apparatus set up, Hertz activated the transmitter. A bright spark here, and across the room, a faint, almost invisible spark mirrored it. He had done it. He had generated and detected electromagnetic waves, just as Maxwell had predicted. He proceeded to show that these waves behave just like light. They could be reflected, refracted, polarized. He even measured their speed and confirmed it was indeed the speed of light. Hertz had proven, beyond any doubt, that information could be sent wirelessly through the air. Asked about applications, he replied, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right." He could not foresee that he had laid the essential foundation for wireless communication, the wireless telegraph, radio, television, radar, Wi-Fi, satellite communications. He had sent the first whisper across the air. The end of the 19th century brought a discovery that would take electronics to a subatomic level. For decades, scientists had experimented with passing electricity through glass tubes from which most of the air had been removed. They observed strange rays called cathode rays, whose nature remained a mystery. Then, in 1897, British physicist J.J. Thomson conducted ingenious experiments with those tubes. He applied electric fields, then magnetic fields, and watched the rays bend, while measuring their properties. He concluded the rays were not waves, but tiny, negatively charged particles, nearly 2,000 times lighter than the lightest atom. He had discovered the electron. For the first time, we understood current not as an abstract fluid, but as a flow of physical particles. That understanding paved the way for the first truly electronic device, the vacuum tube. Building on Edison's observation, the Edison effect, John Ambrose Fleming developed the first practical vacuum tube in 1904. His diode contained 2 elements, a heated filament and a plate, allowing current to flow only one way. It could detect faint radio waves. In 1906, Lee DeForest added a 3rd element, a small wire grid, naming it the Audion. The grid was the key. A small voltage on the grid controlled a much larger current from filament to plate. That made the vacuum tube an amplifier and a very fast switch. The triode enabled long-distance telephony, public address systems, broadcast radio, electronic televisions, and room-sized computers like ENIAC. But tubes were fragile, hot, large, and expensive. The era of the vacuum tube was powerful but cumbersome. Heat, size, power consumption. The search was on for a solid-state solution, amplify and switch without a heated filament or a vacuum. This quest reached its climax in winter 1947 at Bell Telephone Laboratories in New Jersey. John Bardeen, Walter Brattain, William Shockley, studying semiconductors like germanium to replace unreliable tubes in the telephone network. On December 16, 1947, Brattain and Bardeen pressed gold foil contacts onto a germanium slab. They applied a signal to one contact and saw a much larger signal from the other. It worked, the first successful point-contact transistor. Weeks later they demonstrated it, amplifying a human voice. The name transistor, transfer resistor, was chosen. A Nobel Prize followed. The transistor could amplify and switch like a tube, but was tiny, sipped power, ran cool, and lasted long. At first expensive and hard to make, they found early use in hearing aids and military hardware. Manufacturing improved, costs plummeted. In 1954, the first transistor radio appeared, pocket-sized and portable. Most importantly, the transistor unlocked modern computing. Smaller, faster, more accessible. Electronics shifted from hot, glowing glass to cool, solid crystals. A new era of portable, complex electronics had begun. The transistor was revolutionary, but early devices used individual, discrete components. Circuit boards became jungles of wiring, slow, expensive, and error-prone to assemble. As circuits grew to thousands of parts, a tyranny of numbers emerged. Connections failed more than components. A breakthrough was needed. In 1958, Jack Kilby at Texas Instruments proposed making all circuit elements, transistors, resistors, capacitors, from one piece of semiconductor. He demonstrated a crude integrated circuit, a tiny germanium die with etched components, hand-linked by gold wires. Months later, Robert Noyce at Fairchild independently developed a practical approach using a planar process with metal interconnects atop silicon. The integrated circuit, the second great revolution, didn't just shrink electronics. It changed how we made them. Thousands of components could be fabricated at once using photographic printing, making electronics cheaper, more powerful, and far more reliable. Faulty hand-wired connections vanished. The wiring lived inside the chip itself. This began the age of mass-produced, complex electronics. Pocket calculators replaced bulky mechanical adding machines. The Apollo guidance computer showcased the IC's reliability and compact power on the way to the moon. Computing cost plummeted while performance soared, a trend later captured by Gordon Moore as Moore's Law, packing dozens, then hundreds, then thousands of transistors into a single affordable package. By the late 1960s, integrated circuits packed thousands of transistors, but each was custom for a single job. The logical step, one general-purpose chip programmable for many tasks. In 1971, an Intel team led by Federico Fagin with Ted Hoff and Stanley Mazur achieved it. Hired to build custom chips for a printing calculator, they devised a more elegant idea. The Intel 4004, the world's first commercially available microprocessor, put an entire CPU onto a tiny slice of silicon, with power rivaling ENIAC's room-sized electronics. A programmable brain, feed it different instructions, and it becomes a calculator, a game, a data processor, a universal engine for computation. This unleashed the personal computer revolution. Companies like Apple and Microsoft put cheap, powerful brains on desks everywhere. Over decades, microprocessors became vastly more powerful and cheaper, spreading into cars, microwaves, televisions, and virtually every device. This journey reaches its current apex in the device many carry every day, the modern smartphone. Introduced in 2007, it combined a microprocessor with a touch-sensitive screen, cellular radio, Wi-Fi, GPS, and many sensors, powered by a compact rechargeable battery. It is the direct descendant of every milestone we have discussed. Volta's battery provides the power. Ørsted's and Faraday's principles run the tiny motors that make it vibrate. Hertz's waves carry its calls and data. At its heart is a microprocessor, an integrated circuit with billions of transistors, its powerful brain. From a stack of metal disks and salt water to a pocket supercomputer, the history of electronics is shockingly short and profoundly transformative. Every screen we touch, every message we send, every spark of innovation traces back to those first currents and fields. It is a story of curiosity, rivalry, insight, and perseverance, of minds asking better questions and building better tools. We carry that legacy in our hands, and the current of discovery still flows.